What is going on, everybody, and welcome to part 3 of the reinforcement learning with the Bittle robot dog and NVIDIA's Isaac Sim. A lot has happened since the last video, each step a little baby step, sometimes backwards, but overall I'm getting much closer to my end goal, and I'm learning a ton on the way. The very first thing I did since part 2 was try adding a camera to the Bittle. My thinking here was that a camera would be capable of informing the Bittle of, at minimum, the horizon, but also later even more information, such as objects that the Bittle would need to navigate around, and so on. The real Bittle also has a front camera option, so this seemed like a really good next step. So I learned how to attach the camera in the Isaac Sim, and then all that was left was, well, how to access the camera and actually get the data. But we have the camera. Next, for anybody who is following along, I don't believe I ever explained how to change the color. The official way in the documentation just doesn't actually seem to work for me, so the way that I've been doing it is under that looks section of the Bittle dog in the sim. You can change the material color manually there. The main code to get the data from the camera is here, and after running into a bunch of errors and using OpenCV instead of Matplotlib to show it, here's an example of the output. So now that I've got the camera finally working, the first thing I want to do is save a bunch of these frames so that I can use them to train an autoencoder on the imagery. The idea here is once I have an autoencoder trained, I can use the encoder part to encode the imagery from the camera down to something like 4 flat features, for example. If you're not familiar with autoencoders, I did a video tutorial on them, and I'll put a link to that in the description. So now that I've got the data, I whip up an autoencoder. Again, I'm just going to zoom through this. The autoencoder and the concept of an autoencoder is super basic. The idea here is that we're just going to have some convolutional layers, then flattened down to a fully connected choke point that is as small as I can get. To start, I literally just copy and pasted the code from the autoencoders tutorial on pythonprogramming.net. After copying and pasting, I just spent some time changing some of the variables, hitting some errors, fixing those errors, and I was on my way training the autoencoder. Once the autoencoder was trained, I wanted to see both the fully encoded features, of course, and then also the result of decoding back to get an idea for any information loss that's going on. And also just to see how small of a choke point can we get away with. So here are some examples. Essentially, there are 3 photos. This is a 25 feature choke point for the image. So the image is input into the autoencoder, and then it's encoded down to, in this case, 25 values. The first photo that you see is the original. The second photo is a visualization of the 25 values, just in a 5x5 grid format. And the third photo on the bottom is decoded as the original. It's just basically the original image decoded back. So as you can see, there's definitely some noise, some information loss, but that's perfectly fine. All I think I need to capture in these features right now is the horizon, and I think we've done that. Here's another example. I then try to go from 25 features down to 9, retraining the autoencoder, and again, I check some samples, and that also seems fine. And I even did a 4 feature, and again, that seems totally fine for my needs. To be honest, it might even be possible that this can be encoded into a single feature. But right now, I want to see, does this work in the bot in the sim? Unfortunately, it's at this point where I learn how much this camera sensor seems to slow everything down. What you see here is me printing out the frame number per frame in the sim, and this is real time. It's very slow. It's too slow. It looks like about 7 steps per second. We can expect to do millions of steps per model test, and a sufficiently trained model to be about 50 million steps, just a guess. At 7 steps per second, that puts us to 7.14 million seconds. That's 119,000 minutes, 1984 hours, and 82 days. That's a few days too many, in my opinion. If I ever get to training in real life, that is probably something I'll be looking at in terms of time to train. But the point of the sim is to speed up the R&D. The slowdown here appears to all boil down to line 40, which is where we're actually grabbing the camera sensor's values. I don't know any way around this. This has to be done in the loop every step. There's got to be a better way. I'm sure there is. I just don't know it. In my hunt to speed up the camera, I stumbled upon an IMU sensor example. Here you can see me poking this little ant thing, and the sensor values are updating in the IMU sensor example window. If you don't know, IMU stands for Inertial Measurement Unit, and it's used to measure forces on an axis. So also, the real Bittle robot has one. It looked to me like the IMU response rate here was extremely fast, and cherry on top, there was sample code to go with it. In my opinion, the IMU readings are probably even better than the auto-encoded video. At least for now. There are other things that we can get from video that we can't get from an IMU sensor, but for now, this is pretty good. I'd call this lemonade out of lemons. Using the IMU demo script, I start to port over everything to my Bittle, attaching the IMU itself, adding in the code that will let us probe the IMU data, and then printing it out to see if it actually worked. Running everything, it looks like it indeed actually worked, and if I move one of the legs, we can see the IMU data is indeed updating. And we can see it's happening very fast. Around the time that I'm R&Ding the camera sensor, a new version of Isaac Sim comes out with various major changes, and I accidentally delete the entire project directory when uninstalling the older Sim version, so I wind up rewriting the whole agent and Sim code. Not the worst thing ever, though. I kind of already wanted to rewrite it just to clean it up, essentially, anyways, so cool. After doing all of that, I finally have my first working observations and actions environment, along with those IMU readings for the observations, and we're ready to learn some stuff. One of the other additions that I wanted to make was something to better punish for this, like, wiggling jitteriness. Various commenters brought up things like mimicking lactic acid and such. I thought about measuring how wiggly a line was and embarked down a journey of measuring the smoothness of a line, but eventually I went with just simply punishing for every direction change. If you jitter a lot, the punishment is very high, and if you take strides, the punishment is very low. I then worked to apply this, but not only does this take a while, I'm also simultaneously trying to get things like continuous PPO to work, as well as soft actor critic, and even Discrete Delta PPO, as one of the viewers suggested I try, but every move I make takes a very long time to apply now, and weaving each individual algorithm into my current environment is very messy. It would help to convert my environment to a full-on gym inheriting environment, and if I'm doing that, I might as well start using Stable Baselines 3, which will make iteration much faster. Stable Baselines 3 is for reinforcement learning in Python, like sklearn is for general machine learning. The idea is to make reinforcement learning very modular and easy to apply various reinforcement learning algorithms to your problem. To make actual use of Stable Baselines 3, you need to convert your environment to an actual gym environment with, at minimum, an init, step, and reset method. For something like the simulator here that closes very messy, if you just break it, you might also want to have a close method that cleanly closes the environment. Once you've converted your environment, while Stable Baselines 3 does have a quick sort of check-env method, I find this doesn't really fully inform you if things are going to work right, so I went ahead and just made a double check-env to make sure things are stepping and resetting and cycling episodes as we hope. And finally, I get to the point where it works, and now I'm ready to play with some new algorithms and Stable Baselines 3 in general. One of the other early initial things I added in is frame stacking, which is where rather than having a single observation per step, we have a stack of historical observations and the current observation. So there's a slight history of what's been going on. After this, I start training and comparing models across various algorithms like TD3, PPO, and SAC. I also begin testing different hertz/refresh rates. Essentially, how many steps per second does the Bittle do things? I originally was doing 60 since that's the simulator's default, but then I found 30 to be a bit better. I also tinker a bit with forcefully smoothing moves, various frame stack sizes, obviously other hertz rates, and much more. And then this is also where I began poking into Discrete Delta PPO. Since so far this seems to be my best performer, let's cover the concept of Discrete Delta with classifiers like native PPO. Robotics with motors and servos and such is generally seen as a continuous control type of problem. It's not a question of classification like go left or go right. You might have a higher level control algorithm that does something like that, but when you're trying to control servos, it's a question of what position do we want to set the motor to. This is a continuous type problem, and these are much more challenging to solve with gradient descent, just in general. If you can pick any number between -1 and +1, there are theoretically infinite choices. Of course, with many electronic components, they are mapped to values like 0 up to 32,768 or something like that. So this is theoretically actually discrete. But these are way too many discrete values for an actual classifier, and this is why they're considered continuous problems instead. To understand why this isn't treated as a discrete problem, even though it theoretically is discrete, you would want to imagine having training data that shows, based on some input, you want to set the servo to, let's say, 10,000, but the algo picks 10,001. Well, 10,001 would be considered wrong. And this is why we want to treat it more like a regression-style problem rather than a classification problem. But again, this is very costly because treating something this way takes much longer to solve because of gradient descent and just the nature of having near infinite possibilities. So the concept of discrete delta aims to solve this. Consider having 3 discrete deltas, negative 0.1, 0, and 0.1. Think of these like relative values from the current position. Whichever of the 3 classifications of discrete values that the algorithm chooses is simply added to whatever your current position is. So no longer are there infinite possibilities or even 32,000 possibilities, there's really just 3. So imagine your current position is 0.62 and the algorithm picks 0.1. You add 0.1 to 0.62 and you get your new desired motor position of 0.72. If we're acting at 30 Hertz, for example, this means we can go fully in both directions 3 whole times a second, which for our little Bittle is way more than enough. But we might also want some more fine motor control than that. That might even be too fast. So something like 7 bins might work, and here are just 2 examples of some bins or classifications that I have personally tried on this problem. With these, we have some fairly large acting possibilities. We've got some medium and some fine motor control, right? So we have everything from very quick, rapid movements to very subtle ones. And instead of having nearly infinite or even 32,000 possibilities, we have 7. And this is much easier for an algorithm to actually learn. As I get into some of the results, I couldn't possibly show every single version and every single test that I ran. It was easily in the hundreds, but I can at least give some highlights. So first, some of the things that I tried various hertz, so 120, 60, 50, 30, 20, and 10. I tried TD3, SAC, PPO, discrete delta, and continuous. I tried, because I ended up mostly going with discrete delta PPO, I tried various deltas as well as numbers of deltas. So different delta numbers, but then also like maybe only 3 or 5 or 7 or 9 and so on. And then also various movement punishments, more on that in a little bit. And then also frame stacks. So again, the historical observations coming through for the current observation. I tried 3, 7, 20, and 60, for example. So now for what actually worked. The best performing algorithm by far is discrete delta PPO. It is possible though that, because it's discrete delta, it's going to learn faster than something like soft actor critic or TD3, for example, or continuous PPO. So it's possible I just simply wasn't patient enough, and more research is going to be needed there. The deltas that I went with were the following: negative 0.3, negative 0.1, negative 0.03, and so on back to the positives. Again, I tried many different deltas, many different numbers of deltas. So as you can see here, this was 7 deltas that I ended up going with. The hertz was 20. I found the lower hertz tended to do better, but 20 and 10 were pretty equal in performance, and I felt like 20 actions per second was better than 10 most likely. So that's what I went with. And honestly, I have no idea what's the actual realistic hertz that I could achieve on the Bittle. Like physically, I don't actually know. Next, we had movement punishments. The main punishment here being left to right movement, right? What I'm trying to do is develop a straight walking gait. So any movement left to right is a direct punishment. And then I did other various punishments like punishing for wiggles and punishing for just trying to get the gait to be more realistic. So many people suggested before doing things like simulating like lactic acid and stuff like that. And I did find that of all my crazy ideas, the best idea that performed the best was quite literally just a punishment every time the servo direction changed. So the calculation for that is just like 5A basically. It's every single movement that was made divided by the move punish div, and then I just square this. So the move punish div is 80, and then all movements is actually every servo direction change from the last 20 steps. Again, this was just yet another hyperparameter that I tested, but 20 steps is 1 second at 20 hertz. So every single direction change of a servo is a punishment for the last second, essentially. And again, I tried all kinds of different ideas, but this seems to be the one that worked out best. So getting into some of the results now, this is a 7-frame stack discrete delta PPO or DDPPO example, no movement punishment. And it's a good example of what can happen if you don't punish jittery movement, along with an example of how these reinforcement learning algorithms can find themselves in a sort of local optimum for rewards that is going to be nearly impossible for that model to ever break away from ever again into the future. It also looks like it could be a slight abuse of physics in this case. Now, here is a more appropriate gate and walker. This is a 7-stack DDPPO with jitter punishment, and this is about 10 million steps into training. And just to be clear, the console that you see there, the leftmost number is the total reward, and then the other number is the reward for that very specific step. So this isn't the straightest of walkers, but there is a clear gate here. It's the first of the models to really give me any hope that this could ever work. And also, check out this move. About 2 million more steps into training that same model. It's beginning to look pretty good, but the upper legs don't really seem to want to move very much. But honestly, models like this are super rare to get. Most of the time, what I'm seeing is more like true winners like this, and he's not done yet. There we go. As cool as a model that does that to travel might be, I'm really after a regular walking gait. And then there's models like this guy. All I can say here is that reinforcement learning algorithms have no vanity. They do not care how silly they look. And you might be wondering how this model ever learned to do this over something else. And my suspicion is this is probably to blame. I don't know what's going on there, but again, abuse of physics. So this is the model where I finally begin to settle on most parameters. I'm all in on discrete delta PPO, and those parameters that I settled on are the ones that I showed earlier, like 20 hertz, 80 punish div, 7-frame stack, the deltas that I showed earlier, and so on. I like this one a lot. It looks like a realistic gate. There's obviously tons of room for improvement, but this shows a lot of promise, and this is about 5 million steps into training. Unfortunately, this model evolves into this model about 11 million steps in. While the average reward here is better, I'm not really a big fan. It clearly wants to keep a very low center of gravity, and you can also see it's doing this sort of like move, stop, move, stop, move, stop, and it's subtle here, but about 20 million steps in, here's our guy. It's not ideal. It's a very reliable and stable gate, but I'm just not a fan. Yeah, you can even see that when this model does trip itself up, it is capable of recovering and continuing on its way, which, again, is cool, but I'm just not the biggest fan of this gate. For the final Bittle model for this video, I went ahead and added a punishment for the z-axis bounce that's been going on, and this is done in the form of a standard deviation. Specifically, I'm just simply calculating NumPy standard deviation of the z history. The reward is then just a minus equals of the standard deviation, and then I'm dividing again by a standard deviation division, similar to the other divisions that I've done, like with movements and stuff. So the standard deviation is applied to a history of 10. I actually have not tinkered much with making that 20 or any other number. So 10 is just the one that I went with. I basically just ran it in the simulator, looked at some of the outputs, and tweaked that until it was a number that I felt like, yeah, that's how much I want to punish it. So probably more R&D could be done there. And honestly, this one reminds me of some of the earlier models before they became hoppers. It's definitely more of a walker, fairly stable, good reliable rewards. I think the biggest thing that I notice now is that body roll. I am tempted to also punish for the roll as well. We can access that with the IMU, but I'm just kind of weary about how much restriction, and I do kind of wonder if we just let these models go for a few more tens of millions of steps, if things would just smooth out on their own, because it's more efficient. This model is 20 million steps in so far, and the Hoppy model I let continue training and is currently 65 million steps in, still hopping around. So I think to some extent a natural gate would be naturally found, but it's also true that gates in real life are indeed determined by limiting factors like minimizing energy costs and joint wear and tear, and then also just body stability is definitely a thing. It makes sense so that the animal's head and brain isn't just bouncing around, and so vision is stable. So it's tough for me to come up with final decisions about a good balance for rewards and restrictions and stuff, and every time you introduce some new punishment, you run the risk of adverse impacts that you just did not foresee or intend. So anyways, definitely still much more trial and error to get through. I'm definitely still learning a ton of new information and new things. I also appreciate all the comments, lots of great suggestions, and also just Discrete Delta PPO is something that came from a comment. I don't think I would have stumbled on that on my own. So yeah, thanks to everyone for your input. So that's all for now. If you'd like to learn more about neural networks and how they work, there's a book maybe you've heard of called Neural Networks from Scratch by myself and Daniel Kukiewa. You can learn more about that at nnfs.io. Otherwise, I will see you all in another video.